In this presentation, I explore several methods for coping with the excess demand at airports through applying simulation modeling that focuses on how to use the existing airport infrastructure more efficiently. The introduction presents an overview of the importance of solving the airport saturation problem and set out several solution approaches. These are divided into 4 distinct groups. The last option applies operational practices and/or new technology to improve the airport procedures. This alternative includes computer modeling and simulation. The research presents the application of simulation models to the capacity issues at the Mexico City International Airport to demonstrate how potential alleviate congestion. 4 cases will be presented. The lack of sufficient airport capacity to meet the demand caused by the movement of passengers and aircraft, as well as the consequent problem that is generated in the saturation of airports and the delay of the operations, have become a common challenge in major airports in the world. As you see in the slides, the cases in Latin America, Europe, and USA. Studies of air transport systems show that delays and queues on runways begin to grow substantially when the demand exceeds about 80% of the available capacity of the system, as you see in the slide. Note that if the demand is increased, the deterioration of the service is higher on the right side of the 80% limit, but also note that a reduction in the demand on that side generates higher benefits than those presented on the left side of the limit. The solution to the problem of airport congestion should therefore focus on finding ways to reduce the demand capacity ratio. This can be achieved by increasing the capacity, reducing the demand, or combining both options. In general, the solution to the problem of airport congestion have been divided into 4 options. Option A is related to the incorporation of new infrastructure. This option increases the capacity of the entire airport or the capacity of some of its subsystems. The option B establishes mechanisms that reduce the demand for airport services. The option C, although it doesn't diminish the demand, it redistributes operations, which result in greater operational efficiency of the airport. Finally, option D, through operational or technological innovations, also increases the efficiency of the airport. Now, let's briefly review each one of these options. The option A, investment in new infrastructure. The development of new airports or the expansion of existing facilities directly increases the capacity of the system. However, such developments are often difficult due to funding constraints, environmental concerns, and opposition by local communities to the development of new airports, as has been commented before. Also, such developments cannot address the need for new capacity in the short term. For instance, the construction of a new terminal usually requires between 5 and 10 years to be completed. Increasing the capacity of an existing facility may, however, not involve its physical enlargement, as reconfiguration of the existing space may be sufficient. The option B, demand management. The reduction of demand at an airport can be achieved by shifting a portion of it to alternate locations of other modes of transportation. For instance, remote processing. In terms of the airport land side, this would apply mainly to the parking of vehicles, passenger processing, and the allocation of aircraft gates. Relocation of certain air traffic operations. One method to maximize the use of available capacity at the busy airport is to restrict this use to non-commercial flights. To non-commercial flights, such as general aviation operations. Shift short-haul air traffic to other transportation modes. Replacement of short-haul flights up to 500 kilometer distances with other transportation modes may release some degree of congestion at airports with high proportions of such traffic. For instance, high-speed train. Option C. Option C, spreading demand peaks. This concept involves the adoption of certain economic and/or administrative measures aimed at modifying the demand profile to make it free within the limits of available capacity. Therefore, this approach be suitable for situations where further increase of airport capacity is not feasible or very expensive. Market-based measures, peak period pricing and slot auctioning, and the administrative measures are traffic quotas and slot allocation and traffic flow control. The option D, application of operational and technological innovations, is another promising area of increasing airport capacity. For instance, some innovative operational practices could be considered to improve the utilization of airport capacity. For instance, to apply the knowledge of wake vortex behavior to increase capacity for airports with closed space parallel runways. Aircraft technology, tilt rotor technology, as a converting plane on and larger aircraft, for instance, the Airbus A380. As part of the application of technological innovations, development and use of computer models to assess prevailing levels of service and to evaluate possible options to reduce congestions have been widely recognized. This tool could improve the efficiency of airport operations and capacity management. The technique of simulation is one of the most widely used in operations research and management science to evaluate systems. Simulation models commonly take the form of a set of assumptions about the operation of a system. These are expressed in the form of mathematical and logical relationships among its components. They can be used to investigate a wide variety of issues about the real world. These models are used as a tool of analysis to predict the effects of changes in existing systems or as a design tool to predict the behavior of new systems. The AACM stands out as one of the most important airports in the world, since it appears regularly in the world's top 50. In 2015, the AACM was the 45th biggest airport in the world in terms of number of handled passengers and the 20th airport in the world in terms of the number of handled air traffic movements or operations. In order to show the application of simulation models, the next 4 examples are presented. In all cases, the potential benefits of incorporating new technologies or procedures to the AACM were estimated. In the first case, the effect of shifting the proportions of takeoffs and landings performed at the 2 runways of the AACM is analyzed. To do this, different proportions were established by each runway. And then, using a simulation model, the total number of operations performed for each case was estimated. Subsequently, the results were plotted to show the trends and to observe the proportion that gives the maximum value of operations processed. When the model was developed, the year 2003, the real proportions of takeoffs and landings on runways were the percentages shown on the slide. At that time, the AACM served approximately 748 operations between 7 and 24 hours. The results are represented here in a 3-dimensional system. The percentage of landings on the runway 05 left is represented in the y-axis, the takeoffs percentage on the same runway on the x-axis, and the total operations processed in the 2 runways on the z-axis. Although the percentages of takeoffs and landings on the runway 05 right are not indicated in this figure, their values are implicit in those assigned to the runway 05 left. Under the theoretical condition of handling 100% of takeoffs on runways on runway 05 left and 100% of landings on runway 05 right, that correspond to the lower right corner on this figure, the AACM would be serving around 744 to 746 operations per day. However, according to the simulation model, the maximum value of operations, more than 750 operations that is shown in the red area on the figure could be achieved for a proportion of approximately 90% of takeoffs and 90% of landings on the runway 05 left. The real proportions of takeoffs and landings on runways is marked with the yellow star in the figure. Then, the simulation model result could serve to improve the airport efficiency. I mean, to move from this point to this to increase the operations to the maximum value. The second considered case assumes that higher capacity aircraft is used at the airport to move the same number of passengers. In this way, it is assumed that the new aircraft moves the same number of passengers but requires fewer air traffic movements, or ATMs. In order to estimate the queue sizes and waiting times on the runway, a new simulation model was developed. The assumption is that the airlines that operate aircraft ATR 42 at the ACM change their fleet to ATR 72 aircraft. For the considered demand conditions, January 2011, there was no operation of ATR 42 aircraft between 0 and 6 hours. However, for the interval between 7 and 24 hours, 40 landings and 39 takeoffs of aircraft ATR 42 were performed. The results of simulation are shown in this table. Each value estimated is the average obtained from 10 simulation runs. In absolute terms, the reduction of the maximum queue sizes to aircraft is the main benefit. In this condition, the reduction in average queues and average and maximum waiting times are marginal, as you see in the table, less than 1 unit. However, in relative terms, there are significant reductions in queue sizes of around 19% in maximum and average, and in the average waiting time, and the lowest benefit belongs to the maximum waiting time. It should be noted how these benefits are obtained with a reduction in the runway's demand of almost 4%, and that the same number of passengers is transported. This is the case number 3. The International Civil Aviation Organization has established mandatory minimum separations based on the category of vortexes generated, which in turn depends on the aircraft maximum gross takeoff weight. Knowledge of wake vortex behavior can increase capacity for airports with closed space parallel runways separated by less than 2,050 feet. After several decades of research on vortex behavior, wake transport over short times is well understood. In order to increase the capacity of runways with the use of this knowledge, new criteria have been suggested to reduce the current operational limits at airports. The characteristics of the AICM runways indeed fit the definition of closed space parallel runways because the runways of this airport have a separation of 1,017 feet. To estimate the effects of this knowledge in the AICM, it was assumed that the capacity of its runways is increased to 120 operations per hour, in accordance with the operational implications identified by the research of Vernon and Larry. It was determined under this new condition when the congestion problems initiate at the AICM, in which year the demand capacity ratio is equal to 80%. And also, we estimate the value of the corresponding amount of operations at runways. The results are shown in this figure. For each level of demand, 10 simulation runs were performed. The dates in which the different levels of demand will be reached are shown. The first corresponds to the values recorded in January 2011. The others are 60, 70, 80, 19, and 100% of maximum capacity of the runways respectively. These dates were estimated according to a demand forecast. The results show that the saturation is initiated until year 2036, unlike which was estimated with the current capacity when the congestion initiates in year 2015. In other words, with the new technology, the congestion issues could be deferred 21 years more. Okay, the case 4. In this case, the impact of implementing a new policy to serve the operations at runways is estimated. This policy is different from the applied currently in the world, first come, first served, and its purpose is to minimize the passenger delays. The first come, first served rule does not take into account that the operating costs and seating capacities of various aircraft are different. For instance, the operating cost of a Boeing 747 with 452 passenger capacity is eightfold as compared to an ATR 42 with a 48 passenger capacity. And the Boeing 747 can transport 9.4 times more passengers than the ATR 42. Consequently, if the attention sequence of aircraft in a waiting line is reordered, it is possible to obtain savings in operating costs and reduce passenger delays. In this case, 4 simulations were executed with a model. First, applying the current policy, and after with a new strategy. Afterwards, the benefits in terms of waiting time reductions were determined comparing these results. In order to apply the new strategy, it was necessary to know for each aircraft in the queues its specific operation time and number of seats. The operation time for each aircraft was obtained using the information generated by the simulation model, and the number of seats were typical figures established by aircraft manufacturers. The data used in the model reflects the operational conditions of the AICM in year 2011. The results show that if the new strategy is applied, it is possible to reduce the delay waiting time in more than 10,000 passengers a minute. Also, it was noted that the first 6 hours of operation of the AICM only contribute with a 0.46% of the benefits, very low. During this interval, queues of only 2 aircraft were observed. In contrast, after this period, queues of 2, 3, 4, and 5 aircraft were estimated. Now I'm going to the conclusions. The simulation models could help to establish orientation guidelines to achieve a greater efficiency of the airport. For instance, it could be estimated with a simulation model the proportions of takeoffs and landings in order to maximize the operation in airports with several runways, as we see in the case 1. The use of aircraft with greater capacity that replace 2 smaller aircraft could originate benefits in the operation of the airport. For instance, reducing the queue sizes and the waiting times, as we see in the case 2. The application of a new technology to increase the capacity of the runways to 120 operations per hour would produce significant benefits in the operation of the AICM. Under this condition, the congestion of the airport would begin until the year 2036, as we see in the case 3. But it is important to emphasize that the result only reflects the most favorable conditions that occur when there are not dangerous vortices. It was estimated that if a new proposal to serve the aircraft during takeoff and landing phases at the AICM runways is applied, it is possible to obtain reductions in the passenger delays, as we see in the case 4. Finally, although the 4 cases described before were considered in an independent way, they could be integrated in just one case, since they are complementary. In this way, it is possible to obtain a greater efficiency for airport facilities, benefiting passengers and airlines. And I finished. Thank you.